Okay, so just to recap for the video's sake, when we talk about radical expressions, they're basically going to be algebraic expressions or numeric expressions that are enclosed in a root or a radical symbol. Some simple examples would be like 25. When we take the square root of that, that would just return the number 5. Similarly, the square root of 49 gives us 7. So you can think about the square root as asking you to provide the number a that when multiplied by itself gives us back x, the larger number that's inside the square root. Okay. But there's more than just the square root. There's multiple kinds of roots or radical expressions. For instance, you might be asked to simplify this expression, the cube root of 8. And we can sort of expand our definition of the square root and say that this cube root symbol is asking us what number multiplied by itself 3 times gives us 8. So using that definition, when we simplify the cube root of 8, what should the number that we get be?
2.
Yeah. The cube root of 8 is equal to 2 because two times 2 times 2, or 2 to the third power, 2 cubed, gives you 8. So here we have like an important idea. Let me go ahead and box that in. And the idea here is that radical expressions are inverses of exponents. So I think I've done this with you guys in the past, in the before times, before spring break. And that is that in math, you have all these operations. And then every operation has an opposite or an inverse operation. So if I told you, or if I asked you, what is the opposite of addition? What would that be?
Subtraction.
Yeah, subtraction. And what is the opposite of multiplication?
Division.
Yeah, division. Well, now in your arsenal of operations, you should start to like commit this to memory that when you raise something to a power, let's say I'm going to put a number raised to the second power. Okay, and this could be any number, which is why I put parentheses there, but I'll go ahead and throw like the little hashtag or the number symbol. Some number raised to the second power. The opposite of this operation would be the square root of some different number, right? Likewise, if I raise something to the third power, then the opposite operation that will undo this operation is the cube root. So in general, whatever this number here is, I'll just put something to the nth power, because there's an infinite number of exponents that we could possibly use. 1, 2, 3, 4, 5, 6, 7, so on. We could even use negative exponents. But if we raise something to a particular power and we wanted to undo that operation, we would just use the corresponding radical expression or radical operation. And this number, for the exponent, we usually call it the power. But when we're talking about the radical, we call it the index. But in any case, in other countries, they call both of them indices or index because they basically are corresponding to the same exponent. And they will cancel each other out. Okay. Well, it might not be entirely clear what I mean by it will cancel each other out. So let me give you a really clear example of that cancellation happening, or that cancellation happening. So observe this. Observe that if I had, for instance, 4 raised to the second power, that would give me 16. 4 times 4, right? And, just if we're still getting those juices going, 4 raised to the second power. Ooh. Clearly, I'm still getting my juices going. 4 raised to the second power is 16. It's the same thing as 4 times 4, which is 16. Okay, and we want to do an operation on 16 to get us back to 4, to get us back to this number. Well, if I just take this 16 and I take the square root of it, well, then that gives me back 4. So we're sort of back where we started. In the same way that, say that if we started at 10 and I added 2, that would take me to 12. And then if I was at 12 and I subtracted 2, it would take me back to my original 10. Because adding 2 and subtracting 2 are opposite operations. So raising something to the second power does something to this number, makes it bigger by multiplying by itself, and then using the square root takes you back and makes it smaller. And it takes you back to the original number. Okay, but I've been using really simple examples up to this point. These are all nice whole numbers, and I could plot them on the number line if I wanted to. Like I could say this is, let me start at 0, and we'll just stick with the positives. This will be 1, this will be 2, this will be 3, this will be the square root of 16. This will be the square root of 25. This will be 1, 2, 3, 4, 5, 6 would be the square root of 36. Right, and I'm just sort of being a little bit playful here with the number line. We understand that if we were to count this normally, this would be 4, 5, 6, and so on. But we could write those numbers as a radical expression, and it turns out that these radical expressions are really nice because they just give you back a whole number. Similarly, I could think of 3 as being the square root of 9 if I wanted to. 2 is the same thing as the square root of 4. 1 is its own square root, so square root of 1. And 0 is actually the square root of 0. And you could verify this in your calculator if you needed to. And I always recommend that you verify it for yourself in the calculator, right? If we go to the square root of 0, it returns 0. So those are the same value. The square root of 1 is 1. The square root of 4 is 2, and so on. So you could always double check this. Well, these radical expressions line up nicely with the whole numbers because they're equal in value to the whole numbers. But can you find the location of the square root of 2 on the number line? In other words, what do we get when we simplify the square root of 2? Let's just think about that for a second. Well, does anybody know on this number line where the square root of 2 would be if we were to like figure out a place where it most likely would go?
Between the 1 and 2? 1 and 4, the root of 1 and 4.
Yeah, it would be somewhere here, right? And I sort of made this a little bit more confusing by putting some whole numbers over here and some whole numbers over there by mixing and matching. So let me go ahead and clean this up. Let's write that number line out again. I'll put the whole numbers on the bottom. So 0, 1, 2, 3, 4, 5, 6, 7, and so on, all the way to infinity. And that is equivalent to the square root of 0, the square root of 1, the square root of 4, the square root of 9. This is the square root of 16, the square root of 25, the square root of 36, the square root of 49. So we're saying, okay, the square root of 2 must be between the square root of 1 and the square root of 4. And that makes natural sense because something is going on here where these numbers are getting bigger, where we have 0, the square root of 0, the square root of 1, but then they sort of skip around a little bit. The numbers get larger here. We go from 1 to 4, and then from 4 to 9 to 16, 25, 36, 49, 64, 81, and so on. Because like typically we just think about the whole numbers as being on the number line, but really the number line has all these weird numbers on there too. Some of those radicals are equivalent to the whole numbers, but some of these radical expressions are not. So the square root of 2, this is a note, and many other radical expressions are called irrational numbers because they are, one, not whole numbers, or they can't be simplified to whole numbers, and 2, they can't be written as fractions. It's probably been a while since we talked about the number line, but when we introduced the number line, I talked about rational numbers, things that could be written as n over d, where you have some whole number on the top and some whole number on the bottom. Well, it turns out that the square root of 2 and many other radical expressions, they just can't be written as fractions. But we still need to be able to find their location on the number line. So one way you could do that is by figuring out where all of the perfect, these are called perfect squares. And the reason why they're called perfect squares is because when you take the square root, you get a whole number back. The square root of 2, however, is not a perfect square because when you simplify that in the calculator, for instance, so in the calculator, the square root of 2 gives you some ridiculous number. The square root of 2 is 1.414213562. So I'm just going to put 1.414. Why not? 213562, and that goes on forever. This is irrational because the decimal part has no repeating pattern. And trails off forever. So if we were to cut that number off at 1.414, it would be close to the square root of 2. But it turns out that this form, this radical form of the number, is an exact number. Whereas this decimal part is just an approximation. The decimal form is only an approximation. In the same way that, for the number pi, we just say 3.14. Well, there are many more digits. There's an infinite number of digits that are associated with the number pi. And if I put pi in the calculator, you would get only 1, 2, 3, 4, 5, 6, 7, 8, 9 digits in the calculator. But the only reason you get 9 digits here and not more is because the calculator has a finite memory, right? It's limited in its capacity. In the same way that we as humans are limited in our capacity to write out an infinite number of digits, we're just going to cut it short at some point. But when you write the expression just as the square root of 2, you don't have to cut it short. This is understood to be the exact number on the number line. And it turns out that the approximate location is around 1.41. So Yvonne, you were correct that the square root of 2 has to be somewhere between 1 and 2, or between the square root of 1 and the square root of 4. So I could just say maybe it's like right here, a little bit less than half. That's where the square root of 2 goes. Does anybody have any questions about that? It's a little bit weird because we're not dealing with whole numbers here. It turns out that the structure of the number line is a lot more complicated than we originally thought. Okay. So there are two ideas here that we really need to understand. And the first is that radicals, which are sometimes called roots, you'll hear me go back and forth, are the opposite or the inverse of exponents. In fact, we could write them. We can write radical expressions as exponents. And so we'll have some homework problems that will say, write this as an exponent expression. Write this radical expression as an exponent expression. So for example, if I have the square root of x, and remember, there's always an understood 2 for the square root. So I'm going to put a little 2 here. Then if I wanted to write this as an exponent, it turns out I can write this as x to the 1 over 2 power. This is sort of a definition. And we'll think of radicals not only as being the opposite of an exponent, but as being rational or fractional exponents. So radicals are fraction exponents. And why does this make sense? Well, we just said that, when I take number 5, for example, take 5 and then raise it to the second power, you get 25. And then when you square root it, right, the opposite of the second power, then you go back to 5. Well, we could write that out as 5 squared, and then at the same time, I'm going to take the square root of that. And we could write this a number of different ways. I could write it as 25, the square root of 25, but I just want to illustrate what's happening here. Based on this definition, I could write the root part, which is this part, as a fractional exponent so that I can convert this expression to the stuff on the inside is going to stay the same. So I'm going to leave it as 5 to the second power. But now I'm going to say that instead of writing it as a root or a radical expression, then I'm going to write it as 1 over 2 power. And then can anybody tell me what happens when you have a number that's raised to a power and raised to another power? What do I do with these powers?
You multiply the powers.
Yeah. So this was if you remember your exponent rules, power to a power rule. And if we multiply 2 times 1/2, what do we get? What is 1/2 of 2?
I don't know how to say. 2 over 2?
Yeah, but what does that reduce to?
1.
Yeah. So you can see here that when I do this operation to reduce the powers, that reciprocal powers result in 1, or they cancel out. And then anything to the 1 power is just itself. You're just writing 1 copy of that number. So yes, this is sort of a convoluted way of thinking about it, but you can see how the second power and the square root cancel out. So in general, this idea of writing a radical as a fractional exponent is something that you can generalize. So in general, the nth root of x, so whatever number this is, you could convert this radical expression and this goes back and forth. You can convert the radical expression into a fractional exponent by writing x to the 1 over n power. So this is exponential form or an exponential expression. Also, if you have both a radical expression and a power, so let's say that I had the nth root of x to the mth power, then I could rewrite this as x to the mth power over n. And I think it's super helpful to label this that the numerator of the fractional power is going to be considered the power or the exponent. And the denominator of that fractional power, you can consider the root. Okay, so that's enough of conceptual stuff for now. Let's jump into some examples so that you guys can get some practice.
Can I ask something?
Yeah, go ahead.
Okay. In the first examples you gave us for the operation opposite and inverse, it says like if it's a number with a power 2 or power 3, yes, thank you. Is inverse as a root, a square root, right? The first one.
This one.
Yeah.
Yeah, so if the
It
second
is not
power...
like the square root inverse to as the number and elevator for the second power.
Wait, can you repeat that one more time?
Okay, sorry. So the square root to do the inverse form is not supposed. Oh, I understood that it will be like a number in a second power. And
on the inside.
Sorry, my English.
No, you're fine. I'm trying to bridge that language differential, but
yeah, sorry.
No, it's
And then
definitely
you
not your
mentioned that the square root, and one example that you give us is the square root of x is equal to x to the half power.
Yes.
So what happened with the other inverse? That x at second power is the square root.
Oh,
I get confused right there a little bit.
I see. X to the second power
is to the inverse is the square root, right?
No.
No?
So the square root.
So what would
the square root, which has a little 2 here. When you have the root, you have to remember that, and let me use the same color here, that this root becomes the denominator of your fractional exponent.
But what about the bottom, that x to the second power? Is not an inverse to square root? It's a square root and inverse?
Well, if you were to think about this as x to the 2 over 1, so 2 over 1 is the same thing as 2.
No, I mean, the first examples you give us as a square root is the opposite on the inverse. So x at the second power is equal to the square root, right or no?
No.
It's what you gave us in the first example, so that's why I'm a little confusing.
This example.
No, what is the other one that you showed me, the first one? No, the other one that you gave us the first one.
Over here.
Yes, correct, that one. See?
Okay, so what I'm saying with this little chart is that when you have something raised to the second power, that the opposite of this is taking the square root of it. And what I mean by that is that they will undo each other.
Okay.
So the example here that I was trying to give you guys is that, let's say that that I had 7, and then I said, okay, let's take 7 and then apply the second power. What number do I get here when I apply that second power?
It's 49.
Yeah, 49. Okay, and now I'm asking, once I have 49, what operation do I need to do to get me back to 7?
The square root.
The square root. So the square root of 49 takes you back to 7.
Yes.
So if you were to see that played out all at once, that would be like 7 squared, and then you take the square root of that. Rather than, okay, you could do it 2 ways. So the first way is that you could simplify this step by step with little baby steps. You could say, this is 7 squared, and we'll take care of everything on the inside of the square root. So this will be 49. And then you can handle all the square root part, which takes you back to 7. And so 7 would be the simplified version of this original problem. But now that we know about inverses, so this is the inverse perspective. If I asked you what is the square root of 7 squared, then you could say, well, if you take a moment and say that, okay, well, I know that the square root and the second power are opposites, then those will cancel each other out, and I'll just be left with 7. Another way of thinking about it, let me give you another example. The cube root of 27. Does anybody know what that is without using your calculator? Well, one way you could work this is say, okay, I know that 27, that I'm trying to cancel out this cube root. So maybe I could write the 27, I can write the stuff on the inside here as something raised to the third power, so that the cube root and the third power will cancel out. Well, what is the thing that needs to be raised to the third power to give us 27?
3.
Yeah. It turns out that if we just sort of like go in our heads and say 3 to the third power is 3 times 3 times 3, and that's 27, then I can make that replacement. I can replace the 27 in this problem by 3 to the third power, make that replacement. And then I can say, by the property of inverses, the cube root and the third power cancel each other out. So I could cross that out, and I'll just be left with 3. Does that make a little bit more sense?
Yes.
Okay. And again, the other perspective that you could take on this step is you could say, okay, once I've made that replacement and I have the cube root of 3 to the third power, that based on that property of radicals that I gave you, that radicals are just fractional exponents, then what I could do is take this cube root symbol and I'll write it as the 1/3 power. And so I'll leave the 3 to the third power alone. And then I can use my property of exponents here and say that 3, and then I have a power to a power, so I could write this as 3 times 1/3, which I know is going to cancel out to be 1, which will take me back to 3. So it's 2 perspectives on the same operation. And that's what I was trying to get at with the inverses. But I think that once we get some more practice in, it's going to feel a little bit more natural. Because
Okay.
the terminology here is really similar, right? I'm going to tell you square something and then take its square root. And you have to remember that square root and square are not the same operation. They're opposite operations. In the same way that you wouldn't confuse, what is 10 plus 2 minus 2. Addition and subtraction are opposite operations. And we wouldn't confuse those. But then again, those two operations, the words that we use for them don't sound the same. Addition, subtraction sound completely different. Square root and square sound the same. So, I mean, I guess to avoid some of that linguistic confusion, you could say that raising something to the second power is canceled out by the square root or the second root. So roots cancel powers. But in any case, some practice problems just so that we get used to simplifying radical expressions. I'm going to write some of these down. Square root of 49, 2. Negative square root of 289. I'm going to put the square root of 100. And then I'm going to challenge you guys with the square root of 100 over 49. And then also the square root of the negative square root of 225 over 4. Maybe I should challenge you guys some more. I think that these will be pretty straightforward. So let me give you some more. The cube root, go ahead and simplify the cube root of 125. The cube root of 64 over 27. The fourth root of 625. Okay. I'm going to throw you guys into breakout rooms. So just go ahead and accept the invitation once that goes out. I think 2 breakout rooms should be good. And just talk amongst yourselves as you get confused, and I'll be in to check on you in a bit. Okay. Breakout rooms are now live.
and it says second.
Then it turns
and
red.
then it's 1, 2, 3, like 3 or 4 down where it says like X2, you'll see like the root symbol above it.
Oh, okay. So tiny.
Yes.
Okay. And how do you, they're clear. Okay, so.
How are you guys doing on these?
I'm getting done. I just have one left.
Okay, cool. Are we primarily using the calculator to get these?
No, I just used the calculator on my last one.
Okay, cool.
To do the fractions, the number 4, 100 divided 49.
Yeah.
I'm just guessing how to get their square root. I had 2 options. One is divided 100 divided by 44 and then take the square root. And the other one is just take the square root for the top number, and the square root for the bottom. But
yeah. So
I did mine.
So here's a property that I didn't explicitly state, but is going to be super helpful. And this is sort of where I guess you have to get creative with the math. And we've learned this property already with exponents. So we learned that if we have, let me see, that if we have a fraction raised to a power, that power goes onto the top and onto the bottom, right? It turns out that since a radical expression, it can be written as a fractional exponent, that radical expression can be expressed on the top and on the bottom of the fraction. So if I have the square root of a fraction, then I can write that as the square root of the top number over the square root of the bottom number. So that's the property that you want to use. And in reality, these are the same property. Now that I've sort of revealed that radicals are a form of exponents, the exponent rules all apply. So yeah, you'll want to use that if you were doing this one and that one by hand.
Okay. Yeah, okay, thank you.
Okay, I'm gonna jump into the other breakout room just to see how they're doing. How are you guys doing over here?
I'm doing all right. Just like I did have trouble with number 5 and number 7.
Yeah.
Same here. I have trouble with 5.
Yeah. With number 5, whenever you're simplifying algebraic expressions, we have a negative sign here. We have stuff inside the radical symbol, and then we have a fraction. So you want to sort of remember your order of operations and sort of take care of the stuff on the inside first before you move out to the negative sign. So what I would do is like try to simplify the radical of 225 over 4. And one helpful property that I didn't give you, but is going to be super helpful, is that if you remember when we were talking about exponents, I said that if we had exponents, a fraction raised to an exponent, that exponent got applied to the top and the bottom of the fraction, right? So a over b, if I raise that to the nth power, then that would be a to the nth power over b to the nth power. Well, since radicals are like fractional exponents, that property expands. So we can have the radical of, or the root of some fraction, and that's going to be the same thing as taking the square root or whatever root of the top expression and the bottom expression. So technically this could be the nth root, because it's not limited to the second power. It could be the third power or the fourth power or so on. So whatever power, if you have a fraction, you can just take that root of each of the numerator and denominator of the fraction. Does that make sense? Okay. Yeah, so like for example, number 4 would just be the square root of 100 over the square root of 49, which would just be 10 over 7.
10 over 7.
Yeah.
So the other one would be like 15 over 2.
Yeah, and then we would keep the negative sign since it's just hanging out here.
Okay. And then, okay, thank you.
Yeah, you got it. That's interesting. Okay. I think that we're pretty much done with this set of 8 examples. And they, for the most part, should have been straightforward, with the exception of, maybe this property would have been helpful if I had given it to you before we went in. But I like you guys to like sort of fiddle around with things and sort of think about, how am I supposed to go about this thing? Can I use what I've learned in the past to try to create some new math that will make sense? So let's just jump in to the first one. This one's pretty obvious, right? If we just use our calculator, or we just remember that the square root is asking you what times itself gives you 49, then it should be pretty clear that that should be 7. And I think we've seen this one already in earlier in this lecture. This is the negative square root of 289. So what I would recommend is thinking about this as order of operations, that you want to do the stuff in the grouping symbol before you move out to the negative sign out here. So we'll just hold that to the side for a second and just evaluate the square root of 289. You could play that game where you ask yourself, what times itself, I guess what times itself 2 times would give you 289. And maybe, it's 13 times 13. That doesn't work. We need something bigger. 14 times 14. No, I think 16 times 16. Oh, I'm getting there. 17 times 17. Right, 289. So you could play that game, or you could use your calculator to just say, take the square root of 289 to give us 17. Okay. And that'll be the faster way to do it. So we'll just say that this is 17. Remember, once you take the square root and you use it to make this number smaller, you no longer have the radical symbol. Students routinely make this mistake where they will keep the square root symbol, but you've used it, so it's gone. Okay, we do need to keep the negative sign because we have a negative on the outside, so our answer will be negative 17 there. Does anybody have any questions about that one? The square root of 100 is just asking what times itself gives you 100, and that's going to be 10. When I was talking to you guys in your breakout rooms, I said that the extension of this property, where for exponents, where you have a fraction raised to a power, that the power gets applied to both the top and bottom of the fraction, is going to be the same thing that happens when you have a radical expression. If you have a fraction and you're taking some root of that fraction, you can take the root of the top number and the root of the second number, and you'll be good. So this should just be the square root of 100 over the square root of 49, which is going to be 10 over 7. Does anybody have any questions about that one? I think somebody in one of the breakout rooms answered this one. This one will be negative 15 over 2. Does anybody have questions about that one? Remember, the cube root is asking you how many, what is the number multiplied by itself 3 times that will give you 125. So here you could sort of think, okay, 5 times 5 times 5 is the first guess that I would make. And it turns out that that's correct. So 5 to the third power is 125. So that means that the cube root of 125 has to be 5. Now, if you're trying to do this one strictly in the calculator, you can, if you have a TI-84 or something similar to this. Usually there's not a cube root button. You cannot just type 3 and then the square root symbol, because this is going to be 3 times the square root of something, and we want the cube root. So if you're using some comparable device that has cube roots, you would have to go to math, so the math button, and then you would have to scroll down here in the options. Let me zoom in to option 4 so that you get the little 3, the little index of 3 outside of the radical. That is a proper cube root. And then we could just do 1, 2, 5 and get our answer, which is 5. So again, just to show you one more time, we could do that with the math. Go down to the cube root option. And then we could try a different number, say 81. I guess 81 isn't a perfect cube. Let me think of this. Oh, one of the examples that we used earlier in class would have been 27, which gives us 3. So the cube root of 27 is 3. So if you're ever having trouble trying to figure out those these functions in your calculator, I highly recommend coming to office hours, shooting me a message so that we could meet at office hours or in Math World, because there's just simply not enough time to go through all the functions on, you know, whatever calculator device you're using. I'd have to see you guys one-on-one to figure that out with you. Okay, but moving on to the next one. We're going to apply this same property. Let me zoom out. And just take the cube root of 64 and the cube root of 27. So this will be, well, maybe I'll just throw that in the calculator, right? Math, cube root of 64 should be 4. And the cube root of 27 is 3. So this should be 4 over 3. The fourth root of 625, I think, is 5, because if I just guess, 5 times 5 times 5 times 5 gives you 625. I mean, you could have guessed anything here, right? Like if, let's say that you guessed that because this ends in 5, that maybe it was 15. So this tells you something to the 4th power gives you this. So you might have tried 15 times 15 times 15 times 15. And you would have been way too big. So then we just guess a smaller number, right? You could have guessed 10 times 10 times 10 times 10, still too big. And then I'm jumping down to the next multiple of 5, which would have been 5. In any case, there's a way to do this in the calculator as well. And that is, in the math option, you'll see this thing that says x root. It's number 5. Let me go ahead and zoom in. A little X or a little star next to the root. In order to use,
if there's a letter N next to it, does that work too?
Yeah, if there's a letter N, I think it should be the same.
Okay.
But that letter, in order to use that option, we can't go straight to that option first. We have to type in the number that we want. So the index here, 4, and then we go ahead and select that option. And it'll change this to the proper index for that root.
Okay.
And then we can go 625 and then get the correct root out of that. So this is the 4th root. So some notes on, you know, the way you're going to hear me talk about these roots. In the same way that we talk about powers, let me go ahead and special powers, or maybe special names for powers, right? We said that if we have x to the 2nd power or x to the 3rd power, we call this squared and we call this cubed. So we have special names for roots. The square root of x, or the cube root of x. But after that, we get really lazy and we just say, you know, we'll raise something to the 4th power, to the 5th power, to the 6th power. There aren't a fancy, you know, geometric name that we're going to give to the power. Similarly, again, the square root has an understood little 2 that we never write for some reason. But that corresponds to being squared, so we call it the square root. Similarly, the index of 3 on that radical expression corresponds to, or is the inverse of, the cube operation, so that's why we call it the cube root. Okay. But now we need to simplify what I will call non-perfect radical expressions. So we're going to call them non-perfect because they don't simplify to a whole number. So a whole number without a radical symbol. So when we run into things like this, they are, we can simplify them. They're just not going to look simplified all the way. We're just going to process them as much as we can. And so I think that jumping in with some examples will be good. So, I think I just did one. The cube root of 81. Okay. Now you might think like, oh, okay, this guy must be so smart that he just knows that the cube root of 81 is not a perfect radical, or not a perfect root. And that's not true. I just guessed earlier, and I guessed wrong when I was using calculator to go over one of those problems with you guys. I said, okay, the cube root, so math cube root of 81 in the calculator gives us this ridiculous number. So I'm going to put calculator gives us 4.3267 ... because I'm too lazy to write this approximation. So the question that we're asking ourselves here is, how do we simplify the cube root of 81? Can we simplify it? Even a little bit. And obviously the answer to that clearly rhetorical question is yes, right? Otherwise I wouldn't bring it up. But it turns out that we're going to have to think about radicals in a slightly different way. We're going to have to think about them in terms of undoing the exponent, which we've talked about. So let's think about the cube root of 81. Can we write 81 as some number raised to a power?
Would that be raised to like 1/3? So it could be the reciprocal, so it could just be 81.
Oh yeah, yeah. I mean, you could definitely write this root as the 1/3 power. But what I'm asking is, just focusing on this number 81, can we write 81 as something raised to a power?
9, 9 over 2.
Yes, 9 to the power 2. So if I rewrite that expression on the inside of the radical, I could say that, we have the cube root of 9 to the second power. And we would like to cancel out the powers, right? But can we? Or is this third root or the cube root the opposite of raising something to the second power?
Well, I think for the example that you give us before is like dividing the powers.
Oh yeah, I mean, you could do that for sure. But I wanna think about this as like just the direct question, right? Will this index of a 3, will this root completely cancel out the 2? And the answer is that the indices must be the same to completely cancel.
What is an indice?
Indices is just plural for index. So the number that is represented here on the root. So this root needs to match this exponent in order for them to cancel, right? I said that the square root can completely cancel the square operation, and that the cube root can cancel the cube or the third power. So is there another way that we can write 81 as something raised to a power? So I'm going to put a little box here, something raised to a power. And here's where like you might just play this game in your head where maybe we're going to guess what this number is. And maybe it's going to be related to factors of 9, like trying to break it down smaller. So what are the factors of 9?
1, 9, and 3.
Yeah, 1, 9, and 3. 1 tends to not help us. We see that when we wrote this as 9 to the second power, that didn't really help us. Maybe we want to go smaller. So maybe 3 to some power will give us 81. And that's where you might go into your calculator and say, okay, well, 3 times 3 times 3 is 27, times another 3 is 81. So that means 3 raised to the 4th power is 81. So instead of writing this as the cube root of 9 squared, let's go ahead and write this as the cube root of 3 to the 4th power. Well, here I'm running into the same issue, right? These indices, or the root and the exponent, have to match in order to completely cancel. So what I'll do instead is say that, well, this is the cube root. Leaving that alone, we're just still dealing with the cube root. But 3 to the 4th power, I could break out one of the 3's and call this 3 to the 3rd power times an extra 3, right? Or you could think of it as 3 to the 1 power, right? Because if you multiply these together, you still get the 3 to the 4th power. The exponents add. And now part of this looks like it can be simplified. And so we need to use this property of radicals, which is really an extension of our property of exponents, that if you had a times b raised to the nth power, that you could rewrite that as a to the nth power times b to the nth power. That same property works for radicals, that if you have the radical of something times something else, that you can write that as two separate radicals multiplied by each other. So what we'll do is, right here, I'll just say split the radical. So that now we have the cube root of 3 to the third power times the cube root of 3. And for this first factor, the cube root and the cube, the root and the exponent cancel out, leaving you just with this number 3. Now, nothing can cancel over here. So I'll write nothing cancels. So we just have to leave this part alone. 3 times the cube root of 3 is as simplified as we can get this. So I'm just going to give you guys a chance to write this down, and then I'll speed up my explanation. Right? I was trying to run you through the logic of why this makes sense, but when you're actually doing it, you're just going to feel your way through it. Okay, and it's going to go a lot faster. Does anybody need more time to write this down, or does anybody have any questions, comments, or concerns about any part of this? Okay. So some more examples. What if we wanted to look at the cube root of 1296? And we wanted to simplify this expression. Well, one way we can do this is just examine 1296. And what I would say is prime factor it. Prime factorize. So what I mean is build a factor tree. So we're going to see if we can write this as the product of numbers that are raised to powers, because we're trying to cancel out powers. So you might say that this is, I don't know, maybe 2 goes into this. So 2 times something gives you 1296. 1296 divided by 2 gives you 648, where this is a prime number. And we're just going to keep breaking these down. 648 divides by 2. 2 and 3, 24. We can just keep on breaking this down by 2. 162. This breaks down by 2 again. Should be 81. Just to double check, divided by 2. We can divide this by 9. And then the 9s divide into 3s. It's a fairly large factor tree because I chose a very large number. But in any case, we could rewrite this 1296 as 1, 2, 3, 4. There's 4 factors of 2, so that'd be 2 to the 4th power. And then 1, 2, 3, 4 factors of 3, 3 to the 4th power. But since we're trying to cancel out a cube root, we want these powers to be powers of 3. So if you wanted to, I could call this 2 to the 3rd power times 2. And I could call this one 3 to the 3rd power times 3. Does anybody have questions about this so far? Have I confused or lost anybody? Okay, good. Well, because I want to cancel out things that have a 3rd power on them, because that's what the index on this root is telling me that I can do. And because this is multiplication, and it doesn't really matter what order I put this in, these numbers that I'm multiplying, I'm going to put the things that have the cube root first. So I'm going to put 2 to the 3rd power times 3 to the 3rd power. And then we have an extra 2 and we have an extra 3. And all of that is still underneath the cube root. What I'm going to do then is break up this term and this term into their own cube roots. But because these guys don't have an exponent, I'm going to leave them together or put them back together and just multiply 2 times 3 and call that 6. So I will write this as the cube root of 2 to the 3rd power times the cube root of 3 to the 3rd power times the cube root of 6. Sorry about this scratch work over here. So all of this is scratch work. And now I can just simply say that this cube root cancels this cube, and this cube root cancels this cube. So all I'm left with is 2 times 3, and they're no longer inside the radical expressions. They're just the 2 and the 3. But this term over here can't be simplified any further since these guys didn't have a power of 3. So I just need to leave that alone as the cube root of 6. There's nothing I can do here. So finally, I can multiply 2 times 3 because those are just whole numbers that are interacting with each other through multiplication in the conventional way that we know multiplication works. It's not some weird radical expression. So we'll leave this as 2 times 3, which is going to be 6, and then times the cube root of 6, since this guy needs to be left alone. So even though this doesn't look like an exact number, it looks like you could keep going. You have to stop because you've done all that you can do. We have simplified our radical expression, even though this wasn't a perfect radical. Part of it was, and so that part we can process and simplify further by canceling out some of the powers with the roots. But part of it does have to remain in the root. Okay, so these are going to be like the tips for working these problems. prime factorize the number in the radical. Then you're going to rewrite the radical expression so the index can cancel the appropriate power. And then I guess as a note, you may need to multiply some numbers back together to simplify. And those are just the general tips that you would do to simplify these non-perfect radical expressions. Okay, I'm sure that this seemed really weird, but I just want to show you that if we do take the cube root, let's see, cube root of 1296, you get this ridiculously ugly decimal number. And I'm telling you that if you simplify it by hand, you get 6 times the cube root of 6. Well, it turns out that, let's go ahead and do that in the calculator, 6 times the cube root of 6, we get the same number. So this number that's inside the radical is really large, so part of it could be simplified to the 6. And then the part that was left over inside the radical, the cube root of 6, when we multiply 6 times the cube root of 6, you get the exact same value. Okay. Let me give you guys some practice problems. Cube root of 24. I'm sorry, square root of 24. Square root of 75. Square root of 125. The fourth root of 243. The cube root of 64. cube root of 448. Okay, I think that's good. All right, I'm going to throw you guys in the breakout rooms. And